Hello everybody, welcome back to our second lesson. Today we're going to be looking at chapter 5.2, Graphs and Applications of Exponential Functions. The objective of today's lesson will be for us to learn how to sketch graphs of exponential functions in these two particular forms. Also, we will be learning how to use exponential functions as models. Let us first take a look at what are exponential functions. The formal definition of exponential functions are as follows. I have given over here some examples of exponential functions. So some examples are like 2 to the power of x, 0.25 to the power of x, and even 3 over 7 to the power of x, so long as the number a itself is more than 0 and not equals to 1. Hence, some non-examples would be 1 to the power of x, negative 3 brackets to the power of x, negative half brackets to the power of x. I would like to also bring your attention to 0.25 to the power of x. Take note that 0.25 to the power of x is the same as 1 quarter to the power of x. Hence, we can also say that 4 to the power of negative 1 bracket to the power of x is also an exponential function. Likewise, if I were to simplify that to be 4 to the power of negative x, this itself will also be an exponential function. I would like to also emphasize that bracket negative 3 to the power of x is not the same as negative 3 to the power of x without its brackets. Next, we need to be familiar with the irrational number e as well. Like pi, which is an irrational number with the value of 3.14159 and so on, e is also an irrational number with the value 2.71828 and so on. We call fx equals to e to the power of x a natural exponential function. Because e is an irrational number, that's why in algebraic expressions, we usually don't use the letter e to represent any variable. The next thing is the graphs of exponential functions y equals to a to the power of x. We should be familiar with these shapes because we have seen them in Emaths before. Firstly, when a is more than 1, we will be getting a graph in this shape. If a is between 0 to 1, we will get a graph in this shape. Some important things to take note about the graphs is that, first of all, the y-intercept itself is at 1. The reason for this to happen is because when at the y-axis, x will be equals to 0. And when x is equals to 0, we will see that y equals to a to the power of 0. Therefore, any number when power to 0 will actually be equals to 1. This is the reason why the y-intercept is at the value of 1. The next thing that is important about our graphs is that the graph itself is always approaching the x-axis and never touching it. So what we see on the left is that y increases as x increases. This is what we call an exponential growth. And what we see on the right is that as x increases, y decreases. This is what we call an exponential decay. We will now take a look at try 7. On a separate diagram, we wish to sketch each of the following graphs. In part A, we have y equals to 0.44 to the power of x. To decide what is the shape of the graph, we will fall back on what we have just learned, which is this. So, because 0.44 is less than 1, this means that we will be choosing this shape. And because when x is equals to 0, y will end up becoming equals to 1, hence we will have the y-intercept to be 1. This will be the shape of the graph. Let us now take a look at part B. Similarly, we will also rely on the concept we have just covered about the shape. So, because 5.2 is more than 1, we will then be looking at this shape. because when x is equals to 0, y is also equals to 1, hence the y-intercept will be at 1 as well. Now, what about part C? Part C, we have 1 over e to the power of x. Pressing our calculator, we will find that 1 over e is about 0.3678 and so on. This means that it is lesser than 1. Hence, to decide the graph shape, we will be choosing this. Similarly, when x is equals to 0, we find that y is equals to 1. Therefore, the sketch of the graph will be as such. I would like to further discuss about inverse exponential functions. In this question, which is not found from your textbook, Part I requires us to sketch the graph of y equals to e to the power of x as well as y equals to e to the power of negative x. I would like to pull the answer from try 7c, where we were looking at y equals to 1 over e to the power of x. I hope you realize that 1 over e is the same as e to the power of negative 1. Hence, this y function over here is equals to y equals to negative 1 to the power of x, which simplifies to y equals to e to the power of negative x. As such, the graph of y equals to e to the power of negative x will be the answer from try 7c. For y equals to e to the power of x, because e is more than 1, it is going to look something like that. If I would like to provide a better depiction of the two graphs together, it should look like this. So now that we have these two graphs, how can we compare and state the relationship between the graphs? Are there any observations that you can make? So the observation that we can make is that the graphs are reflections of each other about the y-axis and they both pass through the point 0, 1. We can see that the y-axis is like a mirror that reflects the two graphs. And also 0, 1 is the point of intersection. Hence, in part 3, the point of intersection is 0, 1. What we have just seen is the relationship between the exponential function and its corresponding inverse exponential function. Hence, in general, when we have a function y equals to a to the power of x and the inverse y equals to a to the power of negative x, there will always be reflections of each other in the y-axis. Taking note that the exponential function definition still holds where a is not equals to 1 and a is more than 0. I hope you also take note that y equals to a to the power of negative x is equivalent to this. In this next question from exercise 5.2 question 8, in part I, we want to draw on the same set of axes the graphs of y equals to 2.5 to the power of x as well as y equals to 6 minus x. I shall not dwell on the sketch itself. I would like to pay more attention to part 2, where we want to find the number of solutions to the equation 2.5 to the power of x equals to 6 minus x. I hope that you can see that 2.5 to the power of x is the curve that we have drawn, and 6 minus x is the straight line that we have drawn. As such, from the sketch itself, we notice there is only one intersection point. Hence, the number of solutions to the equation will be 1 only. We will now take a look at some problem sums. In try 9, this problem sum is related to radioactivity. The question says that the amount y milligrams of a radioactive substance present after t years is given by this equation. This equation serves as a model to the situation given in the problem sum. The question also states that a is a constant. This means that a is a fixed number. So at the beginning, there were 500 milligrams of the substance. We want to first find out the value of a. To solve this, we need to recognize that at the beginning refers to t equals to 0. So when we substitute t equals to 0 and also y equals to 500 milligrams, we would be getting this equation. Because e to the power of negative 3 times 0 is equals to 1, so we are only left with a equals to 500. That is how we find the value of a. Next, in part 2, we want to find the amount present after 2 years. This would mean that we have to substitute t equals to 2, and then making use of the value of a that we have already found, we will key this into our calculator and find that the value is 274 milligrams. Lastly, in part 3, we want to find the amount that has decayed for 4 years. So when t is equals to 4, we will find that the value of y is 150.59. I'd like to bring to your attention that in the question itself, it says that y milligrams is the radioactive substance present after t years. So the amount that has decayed for 4 years is 500, which is the amount at the start, minus away what is there in the present, and we will get 349. We need to pay careful attention to the wording in the question. Let's take a look at another problem sum. This question discusses about a chemistry theme. It first starts off saying that an object is heated in an oven until it reaches X degrees Celsius. It is then allowed to cool such that theta degrees Celsius, the temperature of the object, after t minutes is given by this equation. This equation is the model for the entire cooling process. So in part I, we want to find the value of X. Right at the beginning of the question, it says that the object starts off at X degrees Celsius. So this means that when t is equals to 0, theta equals to 120 from the calculation using the equation itself. So X is actually 120. Moving on to part 2, the question wants us to find the value of theta when t is equals to 8. It is a simple substitution of t equals to 8 into the given equation. We will be getting 94.3 as our answer. In part 3, we want to find the value of t when theta is equals to 84. So, likewise, we substitute theta equals to 84 instead. Although the manipulation is slightly challenging in this part. So 84 is equals to 20 plus 100 times 0.8 to the power of t over 6. We will first move 20 over to the left and get this equation. Upon dividing 100 over to the left, we will then get 0.8 to the power of t over 6 equals to 0.64. Now the question here is, how do we continue? Later on in this chapter, we will be looking at logarithms. When you have learned about logarithms, maybe you will start using that kind of method. However, at this point, we will have to rely on our understanding from indices. We need to recognize that 0.64 is actually the same as 0.8 to the power of 2. Please ignore this symbol over here. It is 0.8 to the power of 2. So now that we have the same base of 0.8, we will find that t over 6 is equals to 2 by equating the exponents. This is the skill that we have learned in chapter 5.1. Hence, t is equals to 6. In part 4, find the value that theta approaches as t becomes very large. What does very large actually means? And how do we then find out theta? So what we need to understand is that when t becomes very large, 0.8 to the power of t over 6 itself approaches 0. Why are we only talking about 0.8 to the power of t over 6? The reason is because in the given equation itself, t appears in where 0.8 is at. So our main focus and what is affecting the value of theta is essentially 0.8 to the power of t over 6. So what we can do is when t becomes very large, you can try pressing into the calculator different values of t such that it is increasing. So for instance, I can consider in my calculator 0.8 to the power of 1 over 6, to the power of 2 over 6, to the power of 3 over 6, and even going up to 1000 over 6 if your calculator can give you a value like that. What we can see is that the value from our calculator becomes smaller and smaller and smaller. Hence, it actually approaches 0. You will understand this concept in further detail at higher levels of mathematics. So, when t becomes very large, we observe that 0.8 to the power of t over 6 is approximately 0, or to be exact, approaches 0. So because it is approaching 0, we will find that from the equation itself, this section here ends up becoming 0 because 100 times 0 will be 0. Hence, theta actually approaches 20 when t becomes very large. I would like to emphasize on the word approaching. It is not the same as equal. So this is the answer to the question. Now we will look at the last question that we are going to discuss in this section. In exercise 5.2 question 11, we have the graph of y equals to ab to the power of x, where a and b are constants to be found. It passes through 2, 2 and 5, 16. Because it passes through these 2 points will actually satisfy the equation itself. Hence, we will be able to get equation 1, a equals to 2 over b squared, and equation 2, 16 equals to a times b to the power of 5. What we will do next is to use substitution method to actually simplify and get the answer b is equals to 2. Hence, we will then get a equals to half as well. We have now come to the end of today's lesson. Please spend the remaining time in your A-Maths period to complete these questions that I've shown on the screen over here. If there is not enough time, you may continue with it outside the curriculum hours. Regarding the follow-up, please again refer to your respective teacher's preferences. I hope that you will have a good day ahead. Thank you everyone. Goodbye.